The other metals are the metallic elements located between the transition metals and the metalloids on the periodic table. Compared with the transition metals, the other metals are generally softer, have lower boiling and melting points, and are more electropositive. Aluminum is a silver-white metal that makes up 8% of the Earth's crust. Although it is the most abundant metal on the planet, it is never found in its pure form. Instead, it must be separated from other minerals by a complicated electrolysis process. Aluminum is used in millions of products across the globe, and it is the most commercially important of the other metals. It is the main metal in electrical transmission wires. Gallium is a blue-gray metal that is used to produce semiconductors, transistors, quartz thermometers, and low-melting alloys. A compound of the element gallium arsenide can produce laser light directly from electricity. Indium goes into solar and photo cells, transistors, mirrors, nuclear power regulators, and as a coating for high-speed bearings. Tin is a silver-white metal that can be found in nature in its metallic state. Tin has good resistance to corrosion. Tin plating, placing a thin layer of protective tin coating over other metals, is the primary use of the element today. Tin becomes brittle at very low temperatures, and some believe that this property may have contributed to Napoleon's defeat during the freezing Russian winter. Thallium is a poisonous soft silver-gray metal that has no uses in its pure form because it readily combines with oxygen and water vapor to form a black powdery substance. Thallium compounds are used to create low-melting glass and alloys and to make infrared radiation detectors. Lead is a soft silver-blue corrosion-resistant metal that darkens rapidly when exposed to air. Today, lead is used in many products, including storage batteries, solder, metal alloys, and radiation shielding. Lead has been known since ancient times. The Romans used lead to line their aqueducts and make water pipes. But prolonged exposure to this element can be deadly, which may have contributed to the fall of Rome's great empire. Bismuth is a white brittle metal with a slight pink tint. It resists becoming magnetized more than any other metal. It also is the least heat-conducting metal after mercury. Bismuth is used to manufacture metal alloys, acrylic fibers, plastics, electrical fuses, and automatic fire sprinkler systems. All other metals are opaque metallic elements that have relatively high densities. These elements are generally ductile and bendable, like the transition metals, and they also exhibit some very different properties. Compared to the transition metals, the other metals are generally softer and have lower boiling and melting points. Their atoms are more electropositive, meaning that they lose valence electrons more easily than the transition metals. These differences can be explained by taking a closer look at where the other metals reside on the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. And as the atomic number increases, generally, so does the size and mass of the atoms. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of gallium, so it lies in period 4. Meanwhile, an atom of thallium in period 6 has 6 electron shells. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of electrons in their outermost electron shells. These are called valence electrons, and they dictate how elements interact.
Element number 13 on the periodic table is aluminum. The atomic symbol for aluminum is Al. Aluminum, a soft, silver-white metal, is an excellent conductor of heat and electricity. It is also non-magnetic, non-sparking, and the second most malleable metal after gold. Aluminum gets its name from the Latin word alumen, meaning alum, one of the compounds that contains the element. Aluminum is classified as an other metal and lies on the third row of the periodic table, called period 3. Each atom of aluminum consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of aluminum, the nucleus has 13 positively charged protons and 14 uncharged neutrons. Aluminum has 13 negatively charged electrons to balance its 13 protons. These electrons are found in 3 shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed among 2 electron shells. The 3 additional electrons in aluminum determine its unique chemical behavior. The first 2 are found in the sphere-shaped 3s orbital shell. The remaining electron is found in one of 3 lobe-shaped 3p orbitals. Aluminum typically reacts by transferring its 3 valence electrons to nonmetals. Pure aluminum is a relatively reactive metal, but the I-beam shown in this experiment has formed a protective transparent oxide layer on its surface because it has been exposed to air. A small piece of gallium metal, which has a very low melting point, is melted onto the I-beam using a hot air gun, and a syringe is used to scratch the aluminum through the molten gallium. Next, the syringe is used to collect a small amount of mercury. When the mercury is mixed with the gallium, the 2 metals form an amalgam, which destroys the protective oxide coating and allows the exposed aluminum to corrode. This process occurs over a few hours and is shown here in time-lapse. Because of the destructive effect mercury and gallium have on aluminum, they are banned from being transported on airplanes, which are largely made from aluminum alloys. Aluminum is the most abundant metal on the planet, but it is never found in its pure form. Once it is separated from the compounds it is found with, it can be turned into millions of useful products. Aluminum's lightness and durability make it ideal for making everything from vehicle parts to building materials to baseball bats. And since it resists rust, it is also used for making everything from soda cans to nails to the staples in tea bags. Coney Island in New York was one of the first places in the nation to receive electricity. The inventor Thomas Edison ran electrical transmission wires through the park, bringing power to his newly invented incandescent bulbs. We've come a long way since the lights were first turned on at the turn of the 20th century. Today, electrical transmission lines stretch across the country, reaching even the most remote corners. The metal copper was first used for transmission wires because it conducts electricity so well. But after World War II, copper was replaced by aluminum in high-voltage lines. Although atoms of aluminum conduct electricity only about 60% as well as those of copper, aluminum is 3 times lighter. So a pound of aluminum can actually carry twice as much electricity as a pound of copper. Today, almost all transmission lines and many transmission towers are made of aluminum, and delivering electrical power is the single largest used for the metal. These aluminum lines often carry 500,000 volts. When something goes wrong with one of these high-voltage tension lines, it's up to the linemen to make the repairs. And they usually do it without shutting down the power. A daring aerial technique is often used to repair the lines.
It's pretty dangerous, I feel, because you're mixing aviation with electricity. One, you're depending on the helicopter, everything mechanical to go right. If it goes wrong, you're going to drop out of the sky like a rock. If the lineman makes a mistake, you're going to vaporize.
These linemen and pilots are a few of the handful of people in the world qualified to make aerial repairs. But the dangerous mix of helicopters and power lines saves money and time. It takes the aerial crew only hours to make repairs that would take a conventional ground crew days.
This is the span that we want. I'm going to go ahead and come down in between the two 500 kV lines, and we're going to find the damage location, and we'll get ready to start work.
We could actually get too close to a power line and a tree, and the electricity would arc amongst all of us, and we could actually short out the power line and destroy ourselves.
Working on these high voltage aluminum lines is a dangerous job, one that requires special equipment, steady nerves, and years of training. And it takes brave men and women like these to make sure our homes, offices, schools, and everywhere else continue to receive the electricity they need.
Element number 31 on the periodic table is gallium. The atomic symbol for gallium is Ga. Gallium is a soft silver-white metal that is very reflective. Gallium gets its name from the Latin word Gallia, which was a former name for France, where the element was discovered. Gallium is classified as an other metal. It lies in the periodic table's fourth row, period 4. Each atom of gallium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of gallium, its nucleus has 31 positively charged protons, plus 39 uncharged neutrons. Gallium has 31 negatively charged electrons to balance its 31 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Gallium has 13 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The next 10 electrons fill 5 clover-shaped 3d orbitals. And the final electron is in one of the 3 lobe-shaped 4p orbitals. Since the electrons in the 3d orbital are at a lower energy than those in the 4s and 4p orbitals, only the 3 valence electrons in this 4th level shell influence how gallium interacts with other elements. In this experiment, a stream of hot air slowly heats a small quantity of solid gallium, which eventually melts into a liquid. Gallium is one of 4 metals that is a liquid at or very near room temperature. But it returns to its solid state if just a small piece of solid gallium is added to the liquid. Because gallium remains liquid at a wide range of temperatures, it is useful for high-temperature thermometers. It is also used to make semiconductors, transistors, and laser diodes, which go into electronic displays and watches.
Element number 49 on the periodic table is indium. The atomic symbol for indium is In. Indium is a very soft silver-white metal that is shiny and reflective. Indium gets its name from the indigo blue color of its spectral stripe. Classified as an other metal, indium lies in the periodic table's 5th row, period 5. Each atom of indium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of indium, its nucleus has 49 positively charged protons, plus 66 uncharged neutrons. Indium has 49 negatively charged electrons to balance its 49 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Indium has 13 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals, and the final electron is found in one of 3 lobe-shaped 5p orbitals. Since the electrons in the 4d orbital are at a lower energy state than those in the 5s and 5p orbitals, only the 3 valence electrons in this 5th level shell influence how indium interacts with other elements. Here we have a small brick of indium. Listen carefully. When bent, the metal gives a faint crinkling sound caused by the deformation of its internal crystalline structure. Indium is used to coat high-speed motor bearings and to make transistors and other electrical components. Indium is also used to make mirrors and low-melting alloys, and scientists are finding uses for it in blood and lung research.
Element number 50 on the periodic table is tin. The atomic symbol for tin is Sn. Tin is a lustrous, soft, bendable silver-white metal that is very resistant to rust. Tin's unusual atomic symbol, Sn, comes from stannum, the Latin word for tin. Tin is classified as an other metal and lies in the periodic table's 5th row, period 5. Each atom of tin consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of tin, its nucleus has 50 positively charged protons, plus 69 uncharged neutrons. Tin has 50 negatively charged electrons to balance its 50 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Tin has 14 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals. And the final 2 electrons are distributed among 3 lobe-shaped 5p orbitals. Since the electrons in the 4d orbital are at a lower energy than those in the 5s and 5p orbitals, only the 4 valence electrons in this 5th shell influence how tin interacts with other elements. Ordinary tin is a silvery white metal that is easy to work with. A thick piece of tin is shown here being flattened out in a press. When the piece of tin is bent, the metal's atoms, which form a crystalline structure, produce a crackling sound that is known as a tin cry. Since tin does not react readily with oxygen or water, it is often used to protect other metals, such as iron and steel, from corrosion. Tin is also added to other metals to make superconducting magnets. And tin is combined with fluoride in some toothpastes to help fight microbes and tooth sensitivity. Lithuania was the first republic to declare its independence from the Soviet Union in 1990. Following the Soviet occupation, Lithuanian workers made a shocking discovery while digging at a former military base: a mass grave with more than 2,000 bodies. There were few artifacts with the bodies, such as clothing or weapons, so local authorities had little evidence to help them identify the victims. But some tin buttons were finally found among the bones that changed everything. When the workers cleaned the buttons, they found traces of decorations in the tin. These decorations helped archaeologists identify the source of the buttons and the bodies. They belong to one of the mightiest armies in European history, the army of the French military genius, Napoleon Bonaparte. In addition to helping identify the bodies, the tin buttons may actually hold the secret of Napoleon's greatest defeat. In June of 1812, Napoleon invaded Russia. He brought with him the largest army the world had ever seen, nearly 500,000 soldiers. The Russians couldn't hope to defeat Napoleon's army in battle, so instead they retreated. As they fell back, they devastated the land. They destroyed crops and buildings and left little food or valuables behind them that Napoleon and his troops could use. Napoleon was forced to chase the Russian army for months in a deadly game of cat and mouse. The French supply lines were stretched very thin, and the troops began to weaken. By September, the French army had lost 1/3 of its men to starvation, fatigue, desertion, or hit-and-run raids. Finally, the Russian army turned to fight, just 70 miles outside Moscow. More than 100,000 men died in the battle, but neither side claimed victory. Again, the Russians retreated, leaving Moscow empty. Then a fire swept through the city. Napoleon and his troops now had no food and no shelter. By mid-October, Napoleon gave in and ordered his troops to begin their 500-mile march back to France. But winter came early. Soon Napoleon's troops were faced with starvation and fatigue and freezing temperatures. The harsh winter claimed more French lives than the fighting had. Of Napoleon's army of nearly 500,000 soldiers, only 10,000 men survived to make it back to France. Although there was little direct evidence to support it, many believed that the tin buttons on the French uniforms were partly to blame for their casualties. A unique property of tin is that when its temperature drops below 56 degrees Fahrenheit, the shiny silver-white metal turns into gray tin. Although they are chemically the same, gray tin is non-metallic and powdery. It is possible that the frigid Russian winter turned the tin buttons on the French uniforms into crumbling gray tin, rendering them useless and leaving Napoleon's troops even more exposed to the cold. And his crumbling army may have been the victim of crumbling buttons of tin.
Element number 81 on the periodic table is thallium. The atomic symbol for thallium is Tl. Similar in appearance to lead, thallium is a soft, malleable, silvery white transition metal. It oxidizes quickly when exposed to air or water. The name thallium comes from the Greek word thallos, meaning a green shoot or twig, after the bright green line in its spectrum. Thallium is classified as an other metal. It lies in the periodic table's 6th row, period 6. Each atom of thallium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of thallium, its nucleus has 81 positively charged protons, plus 123 uncharged neutrons. Thallium has 81 negatively charged electrons to balance its 81 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Thallium has 27 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The next 14 electrons are distributed among 7 lobe-shaped 4f orbitals. The next 10 electrons fill 5 clover-shaped 5d orbitals. And the final electron is found on one of the 3 lobe-shaped 6p orbitals. Since the electrons in the 4f and 5d orbitals are at a lower energy state than those in the 6s and 6p orbitals, only the 3 valence electrons in this 6th level shell influence how thallium interacts with other elements. Thallium is exceptionally toxic. A few crumbs can kill, so gloves and secure storage are necessary. This sample of thallium is cut to reveal the pure element. When freshly exposed to air, thallium soon develops a bluish-gray tinge that resembles lead. If it is exposed longer, a heavy oxide builds up on the surfaces, eventually turning pieces of the metal black, as you can see on the outside of this sample. Before it was banned for household use in 1974, thallium sulfate was used as a rat and ant poison. Several other thallium compounds are used in devices that detect infrared radiation and thallium combined with other elements forms low-melting glass. There are no uses for metallic thallium because pure thallium quickly combines with oxygen and water vapor from the atmosphere and forms a black powdery substance. Element number 82 on the periodic table is lead. The atomic symbol for lead is Pb. Lead is a dense bluish-white metal that is very soft and pliable. It is corrosion-resistant and a poor conductor of electricity. Lead gets its unusual atomic symbol, Pb, from the Latin word plumbum, which means plumbing, because lead was often used in ancient plumbing systems. Lead is classified as an other metal. It lies in the periodic table's 6th row, period 6. Each atom of lead consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of lead, its nucleus has 82 positively charged protons, plus 125 uncharged neutrons. Lead has 82 negatively charged electrons to balance its 82 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Lead has 28 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The next 14 electrons fill 7 lobe-shaped 4f orbitals. The next 10 electrons fill the clover-shaped 5d orbitals. And the final 2 electrons are distributed among 3 lobe-shaped 6p orbitals. Since the electrons in the 4f and 5d orbitals are at a lower energy than those in the 6s and 6p orbitals, only the 4 valence electrons in this 6-level shell influence how lead interacts with other elements. Pure lead has a beautiful silver appearance, but it tarnishes quickly when it is exposed to air. Lead's low melting point of just over 600 degrees Fahrenheit makes it an easy metal to work with. The lead here is heated and poured into a 2-chamber metal mold, where it soon cools and solidifies into the shape of the mold. Lead is poisonous and builds up in the human body over time, so it is no longer used to make toys, wall paints, pencils, or other products that might come into direct contact with people. Lead is most commonly used in the production of lead-acid batteries, such as those found in automobiles. Its high density makes it a good shield against X-ray and gamma-ray radiation, so it is often used in X-ray machines and nuclear reactors. Lead is toxic, and repeated exposure can lead to poisoning, which can be fatal. The use of lead has been traced to the ancient Egyptians around 4000 BC. The Egyptians used black eye makeup made of ground lead ore mixed with oils. Other ancient peoples used lead to make corrosion-resistant glazes for ceramics, works of art, ornaments, and even weights for fishing nets. But lead may have been partly responsible for the downfall of one of the greatest civilizations of the ancient world, the Roman Empire. The Romans created a highly advanced civilization. They were particularly good at redesigning and improving inventions of other civilizations. One such invention was the aqueduct, a system that brought clean water from distant mountains to cities and towns. Parts of these aqueducts were rows of arches that used gravity to transport water through lead troughs running along the top arch. The stone arches were especially useful for carrying water across low plains, valleys, and riverbeds. But most of the aqueduct system was a series of underground pipes made of clay, bronze, or lead. These pipes and conduits sometimes stretched as long as 40 miles. Once the water reached Roman cities, it was distributed through lead pipes to public fountains, government buildings, and private residences. Many Roman drinking vessels and cookware were also made of lead or coated with lead glazes. The Romans even used lead powder to preserve food and improve the taste of wine. Some historians believe that the Romans' widespread use of lead may have poisoned them slowly and may have contributed to the downfall of their empire. Modern-day scientists have discovered that even small amounts of lead can be dangerous to consume. The human body cannot distinguish lead from calcium, which is an important element for healthy bones and other body functions. As a result, the body does not get rid of lead once it gets into your system. Over time, this lead buildup can be extremely harmful. Lead poisoning can bring about stomach pain, nervous system disorders, and it can cause damage to the kidneys, red blood cells, and brain. Eating lead is especially dangerous for young children because it can affect their developing brains and cause learning, visual, and motor problems. Over many years, the Romans' ingestion of lead could have built up to dangerous levels, leading to physical and mental problems, and contributing to the eventual collapse of their once great empire. We may never know everything that led to the empire's fall, but it seems clear that the Roman love of lead may have played a part.
Element number 83 on the periodic table is bismuth. The atomic symbol for bismuth is Bi. Bismuth is a soft, heavy, brittle, silvery white metal with a pinkish tinge. The name for bismuth comes from the German term Vismasse, later changed to bismuth, meaning white mass. Bismuth is classified as an other metal. It lies in the periodic table's 6th row, period 6. Each atom of bismuth consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of bismuth, its nucleus has 83 positively charged protons, plus 126 uncharged neutrons. Bismuth has 83 negatively charged electrons to balance its 83 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Bismuth has 29 more electrons than xenon. The first 2 electrons are found in the sphere-shaped 6s orbital shell. The next 14 electrons are distributed among 7 lobe-shaped 4f orbitals. The next 10 electrons fill 5 clover-shaped 5d orbitals. And the final 3 electrons are distributed among 3 lobe-shaped 6p orbitals. Only the 5 valence electrons in the 6s and 6p orbitals influence how bismuth interacts with other elements. Here, molten bismuth is poured into a metal pot. It is left undisturbed to cool, which allows crystals to form. The metal starts to solidify from the outside in, leaving a molten pool in the center of the pot. Once the bismuth has partially solidified, the remaining still molten metal is poured off to reveal the formation of small solid crystals. The bismuth crystals are iridescent. The colors result from the interaction of light and a thin layer of bismuth oxide, which forms on the surface of the hot crystals upon contact with air. Bismuth was once used in some medicines and early printing presses. Today, its main use is pharmaceuticals. It is also common in low-melting alloys. Bismuth expands when it solidifies, which reduces the alloy's tendency to shrink from a mold or form cracks. Compounds of bismuth go into pigments in paints and cosmetics.